Hello and welcome to the screencast for Chem Activity 35, Constitutional and Geometric Isomers. Subtitled, Are They Identical or Are They Isomers? Don't you love the subtitles? This is Dr. Michael Garud, and this is a screencast for Chemistry 120, Allied Health Chemistry at Missouri Southern State University. So Model 1 shows some things that we've seen before, and a little bit of an extension, but some Lewis structures, some stick structures, some ball and stick structures of some molecules. If you would pause the video now and answer critical thinking question number 1. Pause now. Okay, so we are looking at the Lewis structure column right here. And if you count the number of covalent bonds for each carbon, you'll see they have 4. 1, 2, 3, 4. Even in this case where there's a double bond, the carbon has 1, 2, and a double bond makes 3 and 4. Okay? Question 2. In skeletal representations, okay, so that's in this first column, the hydrogens are not shown. Explain how it is still possible to tell how many hydrogen atoms there are on each carbon. Pause the video and write a sentence. Pause now. Okay, did you say something like this? There must be enough hydrogens to make it so that the total number of bonds is 4, or something of that nature. If I look at this carbon, for example, I see that it has 1 line to the left, 2 lines to the right, so that's 3 bonds, so it must need 1 hydrogen to make 4. If I look at that in the Lewis structure, I see that that's the case. The hydrogens aren't shown here, they are shown here, but you can figure it out. So let's apply that. Number 3, draw a Lewis structure representation of the molecule for which a skeletal representation is shown below. Pause the video and draw a complete Lewis structure. Pause now. Alright, I haven't completed the Lewis structure, but if you're stuck, notice there are 4 carbons in this ring and a 5th carbon over here. So I've connected those 4 carbons into the ring with the 5th carbon over here. Sometimes students will note that there are 5 carbons and they'll put the 5 carbons in a straight line, and what they're missing is that you have to connect the 4 in a ring when you draw the Lewis structure. You can't break open the ring to draw the Lewis structure. So don't do it like this. Start with something like this, and when you pause the video, in 2 seconds the answer will appear. So if you want the chance to try this yourself, pause now. Okay, so here is an answer. I've completed the double bond by putting 2 bonds there. Then I've just added enough hydrogens to each carbon so that they have 4 bonds. And this is a Lewis structure. If you drew yours like this, this is a correct structure, but it is a condensed structure, not a Lewis structure. So you get the idea of the difference. Here are 3 different ways you can draw this particular molecule. So that's a skill you'd like to work on, being able to convert between stick structures and Lewis structures and condensed structures. Let's move on to Model 2, constitutional isomers. So you see 2 columns with structures filled in and molecular formula only filled in for one of them. Question 4 says, complete the model by writing in the missing molecular formulas in both columns. So you need to know the total number of carbons and hydrogens for each of those molecules. So pause the video, figure that out now, take as much time as you need, and fill in those 5 values. Pause now. Okay, do your answers match mine? If they don't, pause the video again and go through and count again and try to see how I got where I got. Notice that anytime you have an end, that's going to be 3 hydrogens. Anytime you have something that's just in the middle of the chain, that's going to be 2 hydrogens. Right? If I look here, I see 3 lines coming out from it, so that means there's 1 hydrogen. If I look at this carbon, there are 4 lines coming out, so there are no hydrogens there. So you can figure out how many hydrogens there are by just counting the number of bonds or lines coming from a particular carbon. Number 5. What do the molecules in a given column have in common with the other molecules in that column? Pause the video and write a sentence. Pause now. So I wrote, they have the same molecular formula. Perhaps you wrote something different. This is probably the best answer. Why is it the best? Because the title of the column is molecular formula, and that's the thing that's the same. So that's certainly the most straightforward answer because it uses the words directly in the model and says exactly what it is that's the same using those words. You could have written other things. Some things, you could have said they all have carbon and hydrogen, right? Or you could have said they all have the same numbers of carbons and hydrogens. That would have been correct. It's just simpler to use the words that are already provided for you in the model. Number 6. What do the molecules in a given column not have in common with the other molecules in that column? Pause the video and write a sentence. Pause now. All right, so you got this one, right? After my little pep talk on number 5, the easiest thing to do is to look at the title of the column. Title is structure, so I can say they have different structures. Now you could say other things. You could say they're branched differently. That would take care of this column. I think that applies to this column as well. You could say they have different connections. The atoms are connected differently. There are different ways of saying that, but the simplest is just using the title of the column. They have different structures. Number 7. All the structures in a given column are, and here's a term in boldface, so obviously that's important, constitutional isomers of one another, but the structures in column 1 are not constitutional isomers of the structures in column 2. Based on this information, write a definition for the term constitutional isomers. Remember our pep talks. Pause the video and write your sentence. Pause now. Okay, you got this, right? Pat yourself on the back. Constitutional isomers are molecules with the same molecular formula, but different structures. So you see how we were guided to coming up with this answer. So let's apply that. If the molecule shown below were placed into Model 2, would it belong in column 1 or column 2? Circle 1 and explain your choice. Pause now. So did you determine its formula? That would be the way to go about this. If you determine its formula, you find out it has 5 carbons and 10 hydrogens, so therefore it belongs in column 2. All right, let's move on with Model 3. Representations of methyl cyclobutane. So that is this molecule that we just looked at, this guy, and some different ways of drawing it. A skeletal, a wedge and dash with the hydrogen shown, which we can do if we really want to. Oftentimes with the skeletal, we don't show the hydrogens, but we can. I'm calling this a perspective. You have to imagine that you're now turning this square up on its side and looking at its side. And then we have the ball and stick. So just 5 different ways of looking at methyl cyclobutane. Then we have Model 4. 1,2 dimethyl cyclobutane, shown with the ring carbons numbered 1 to 4. And there seem to be 2 of those, A and B. So critical thinking question number 9. Do the molecules in boxes A and B of Model 4 meet your definition of constitutional isomers from question 7? And explain. Pause the video and write a sentence. So did you say yes or no? I'm giving you two options here. You can say yes or no, because it probably depends on, well, I think you can tell that they have the same formula. But maybe you're struggling with, do they have the same structure or do they have different structures? So at this point, you may have said either yes or no. If you said yes, you said they have different structures. If you said no, they have the same structure. Let's work through that and see if we can figure out if we would classify them the same or different. All right, so let's start with number 10. Carbon 1 in box A, right here, is bonded to two carbons in the ring, a methyl group. So two carbons in the ring, carbon 2 and carbon 4, a methyl group, and a hydrogen. The hydrogen's not shown. So other than bonds to carbons within the ring, what two groups are bonded to each of the following carbons? So don't count the ones in the ring. What are the other two groups? And I'll give you a hint. They're either methyl groups or hydrogens, right? So pause the video and go ahead and answer A, B, and C. Pause now. All right, so you got this. You notice that carbon 1 and carbon 2 in each box are connected to both a methyl and a hydrogen. So far they seem pretty much the same. Number 11 suggests that you use a model kit. And when I do this in the classroom, I have students make models of each of these, one for each. If you have a model kit, you should do that. If you don't have a model kit, or even if you do, I've found, well, let's take a look at this. Okay, here is a model of one of those molecules. So can you tell which one it is? Is this one right? Because it has one methyl group at the bottom, one at the top. See it? All right. And then okay, here is the other one. All right. Do you see it? It has both of the methyl groups at the top. Looks like this one. So the question you're trying to determine the answer to is it possible to twist the bonds in the models so that you can make these identical? The question is, can you take this methyl group here and move it down here where this hydrogen is by just twisting around it so that you can make it to be like this? And I think that even if you don't have the models, you can tell by looking at this that that's not going to work out, because when you try to twist it, you would put so much strain on this central ring, and you'll just, if I try to bring this one up here, it's just going to put that hydrogen into the middle. It's not going to work. So the answer is no, it's not possible. So what you're discovering here is that even though each carbon in box A and box B is bonded to the same four groups, and the molecules have the same connections, chemists call that connectivity, they're in fact different molecules. They're not the same molecule. So this molecule, where the two methyl groups are on opposite sides of this four-membered ring, it's not the same as this molecule where the two methyl groups are on the same side of that four-membered ring. So they're not conformers. You cannot rotate the methyls around to be in the same place, so therefore they must be a new kind of isomer that we haven't seen before, and we're calling those geometric isomers. They're also referred to as cis-trans isomers, and in this paragraph it defines what cis and trans are, or we're about ready to define what cis and trans are shortly. According to this paragraph, if two groups are on the same side of the plane defined by the ring, then that's considered to be cis. And if the groups are on the opposite sides, that's considered to be trans. So what you're supposed to do next, critical thinking question number 12, label one box in model 4 with the name cis 1,2-dimethylcyclobutane and the other one with trans 1,2-dimethylcyclobutane. So pause the video, and on your paper, label these boxes. Pause now. Right, so you have the first one is trans, the second one is cis, correct? When cis and trans are written in print, they usually put them in italics, this kind of font, italics. When we're writing in handwriting, it's pretty difficult to make a distinction between handwriting and italics, and so we underline them. That serves the same purpose as writing them in italics. So they're the same name, but with this prefix cis or trans, which determines the orientation of those two methyl groups. And then the next part of this question says, add perspective representations into each box. So if I page up here, where I can see the perspective representation, I've left you enough space here to write one of those into the box. So pause the video and draw those now. Alright, so hopefully you're seeing that the perspective box is supposed to be what it looks like when you turn this box up on its side and you're just drawing the square, which now looks like a rhombus or a parallelogram, in fact, on its side. Alright, so if I'm looking at this molecule, then you're trying to arrange it in a way so that you can draw the square on its side, and then you can see the methyl and the H and the H and the methyl. So what I've tried to do in that is I've drawn the methyl, and see how I've had to draw the H kind of down here through the ring and below there, which is trying to indicate I'm looking at it on the side, and you can sort of see that H sticking right down here. Okay? And then over here, put the two methyls on the top, the H on the bottom, and that final H, again, if you try to stick it in here, that's probably not working as well as, oh, this is going to be tough. As if you just put it down here like so. And again, that's trying to indicate so you're trying to draw it so that you're showing the ring on its side, the two methyl groups at the top, the two hydrogens at the bottom. Hopefully that makes sense. Number 13. In the space here, draw wedge and dash and perspective representations. All right, so wedge and dash and perspective of cis and trans 1,3-dimethyl cyclobutane. Pause the video and draw those now. Okay, I've drawn a couple of options for those. Pause the video and compare your answers with mine. Yours might not look exactly like mine, but they should be consistent. Notice how if I draw the cis, I can draw both wedges, which indicates the methyls are both on the top, or both dashes, which indicates the methyls are both on the bottom. And remember, we were supposed to do 1,3, so if I have 1, 2, 3, 4, the methyls are on 1 and 3 in this case, not 1 and 2. Now this is still the one with 1 and 2, but if I'm looking at it like this, my perspective diagram has the two methyls on the top, so that would be the wedges. And if I just flip it over, it has two dashes. They're still on the same side. So whether I show two wedges or two dashes, it's the same molecule, just flipped over. Right? Here's two dashes, and here's two wedges. Number 14. Arrange the following descriptive terms in order from the most to least similar, and there are a bunch of terms. So pause the video, take as much time as you need, and arrange them from the most similar to the least similar. Pause now. All right, compare your list with mine. I think you would agree that the most similar would be identical. Here's an example of two structures that would be considered identical. This is cis 1,3 dimethyl cyclobutane, and so is this. They're identical. It's just that you are looking at them from the other side. Conformers, remember, are the same molecule, but you have twisted or rotated around single bonds. In this kind of diagram, we don't really have information about rotating around bonds. In order to have that kind of information, you would need to have a Newman projection, or you need to have a more specific wedge and dash. So you don't know if these appear to be identical. Geometric isomers is another term for cis and trans isomers. So this molecule, the cis, and this molecule, trans, are geometric isomers. In order to have geometric isomers, you have to have them in pairs, right? A cis and a trans. Constitutional isomers we defined those previously in this activity, the same formula but different structures. And I can actually make that a little bit more precise and say different connectivity. And finally, different molecular formula, those would not even have the same formula, those would not be isomers at all. So one thing that would probably be helpful for you to do is to kind of have your own definitions of these terms in your head so that when you read them, you can have a definition that you can then apply. So if I write these terms down and put them on a list, identical, right, would be the same molecule in the same conformation. Conformers are considered to be the same molecule, but they're in a different conformation, and that conformation is arrived at by rotation around single bonds. And you can go back and look at some examples in the previous chem activity of those. For example, pentane, I'll run out of space there. That's also pentane, right? But in this case, this bond is rotated up to here, and so that's conformers. Geometric isomers we've done today. Those are also called cis-trans isomers. In order to have those, you have to have two groups that are either on the same side or opposite sides of a plane, cis-trans isomers. That's what we've looked at today. It turns out there are two different ways to get cis and trans isomers. One of them is in the ring structures that we've looked at. So you can have two groups that are on the same side, which is cis, or two groups that are on opposite sides, which is trans. But there's another way to get cis and trans, and that's when you have alkenes, double bonds, because you also cannot rotate around those double bonds. So if I put two groups on the same side of a double bond, and you'll remember we saw this in the equilibrium activity. I think that was 23A, the equilibrium activity. We had cis and trans, and you can't rotate around those at room temperature. This would be called cis. We haven't learned to name it yet, but I'll just tell you, 2-butene. That's our next chem activity. And then if you have the double bond where the methyls are on opposite sides, and I didn't draw that bond very nicely, so let's try that again. Okay, this would be called trans 2-butene. And the same and opposite is by looking at an imaginary line that goes right down the middle of this double bond. And here my main chain stays on the same side of that. And here my imaginary line or my main chain crosses over my imaginary line. Trans means across. So like when you say transatlantic, that means or transoceanic, it means you go across the ocean. Right? So trans meaning across, cis meaning the same side. If I drew these in stick structures, they would look simpler, just like this and like this. But it's important to know that when you put the double bond there, you can't simply rotate around it. And so if I have this and this, let's draw that one again. We saw this also. This is butane. This is butane. And these are the same molecule because you can rotate around a single bond to get this. But you cannot rotate around a double bond. So these two are both butane, so you would call them conformers. They're the same molecule with rotation around single bonds. But when you put the double bond in there, you restrict the rotation, so now you have geometric isomers. One of them is cis and one of them is trans. So you can have geometric isomers in two ways: when you have rings and when you have double bonds. Those are the two types. Then we have constitutional isomers, which we define that in this activity, right? The same molecular formula, but different structures, and I'm going to use the word connectivity because that's more specific than structures. These cis and trans have the same connections, right? They're both methyls, they're on carbons 1 and 2, so the connections are the same, so you can't call them constitutional isomers because they have the same connections. So that's more similar than constitutional, which have different connections. And then finally, if they don't have the same formula at all, they're not isomers. I titled this worksheet isomers, but really the only ones that are really considered isomers are these two. So maybe it would be better to title it relationships between structures. There is one more kind of isomer to learn, which we haven't learned yet. But maybe you'd like to know that there's only one more, so it doesn't get too much more challenging than this. Okay? That takes us to the end of this activity, the end of Chem Activity 35. So your exercises are applying these terms to these pairs. And as I always suggest, do them one at a time, check your answer, and let me give you a hint. So this is a hint. If you are stuck, what you should do is you should try to name the structure. Now we haven't learned how to name all of these yet, but most of them we have, I think, except for the alkenes, which we'll learn tomorrow or in the following chem activity. So try to name them, because if they come up with different names entirely, they can't be isomers. If they come up with different connections of the groups, right, that's going to give you a hint. So if you are stuck at determining what they are, try to name them. If they both come up with the same name, then they have to be either identical or conformers, because those are the same molecule. If they come up only different in cis or trans, you've defined geometric. And if they have, let's say, a different base name, then they're constitutional, or different branching, constitutional. So that's a hint. You can figure it out just by looking. If you're stuck, try to name them. Do them one at a time. Check the solutions. Email me with any questions. Cheers.